Dear students, today we will discuss about a very important theory in electrochemistry that is known as the Debye Huckel theory. So you already heard about this theory. You may have some fundamental knowing some fundamental things about this Debye Huckel theory. So basically I am going to explain the first what is the background of Debye Huckel theory, or what is the necessity of Debye Huckel theory, and then I will go to the equation and then the interpretation of the Debye Huckel theory. Okay, so in the last class I told you about a very important concept of activity and activity coefficient. There we have discussed a coefficient called mean activity coefficient. So why it is mean, I already explained. That means there are positive ions and negative ions. We cannot measure positive ions only. We cannot measure the activity coefficient of positive ions only or negative ions only. We can take only a mean of that. That is known as the mean ionic mean activity coefficient. So how can we determine mean activity coefficient? So we had some geometrical numerical thing we already discussed, but how can we quantify this activity coefficient? That is a very important problem in electrochemistry. So we have to quantify this mean activity coefficient. Okay, so there you can seek the help of Debye Huckel theory. So Debye Huckel theory actually quantifies the quantitatively you can find out the mean activity coefficient by using the Debye Huckel theory. So how can we reach in the Debye Huckel theory? What is the background of Debye Huckel theory? That is the thing we are going to discuss today. Okay, so for that I am taking a very familiar thermodynamic term called chemical potential. So you are aware of this thermodynamic term, and it is represented by mu, chemical potential. And also there are two types of solutions. You can call it as, one is the ideal solution and other one is the non-ideal solution. So we are talking about the electrolyte. That is why we are considering this solute plus solvent combination, ideal solution and non-ideal solution. So what will be the chemical potential of an ideal solution? You see, in the case of ideal solution you can write mu. Suppose the species is A, mu A is equal to mu 0 A. Mu 0 A is a standard chemical potential plus RT ln. What is that? I am just taking A. That is why I am just writing the concentration of A. So that is the ideal case. So here A you can also express in another concentration term called XA. XA is the mole fraction. So you can also express this equation like this: mu A is equal to mu 0 A plus RT ln XA. So that is about the non-ideal case. So what about this ideal case? What about the non-ideal case? So I told you already about this coefficient, mean activity coefficient. It is coming from the concept called activity. I told you that activity is the perceived concentration, or it is also known as the effective concentration. So there are two types of concentration. One is the perceived concentration, other one is the real concentration. So what is the relationship between all these things that we already discussed? This mean activity coefficient is the ratio of the perceived concentration divided by the real perceived concentration into the perceived concentration divided by the real concentration. Perceived concentration divided by the real concentration. Suppose it is for the species A, you can write AA by CA also you can write in concentration brackets. Okay, so this is the case when you are talking about a non-ideal solution. In ideal solution you can directly write this concentration term, but in the case of non-ideal solution, that means the most of the electrolytes fall under non-ideal solution. There you need the extra you have to consider the concentration term called activity. So that I already explained in the last class. You can check my class on activity and activity coefficient regarding this. So non-ideal case, how can we write then? Okay, in the case of non-ideal situation, suppose it is mu A. I am writing mu A in the case of non-ideal situation, that is the mu 0 A plus RT ln A is the activity. And you know that from this equation you know that this AA activity that is the perceived concentration is equal to our concentration, the concentration of real concentration of A into gamma plus minus, or otherwise you can write here for the simplicity you can write gamma A. So you see here this term AA, that is the activity is equal to the real concentration into our activity coefficient. So our equation will become mu A is equal to mu 0 A plus RT ln, okay, correct, RT ln A plus RT ln gamma A. So this is the situation when you are going to non-ideal systems. Okay, so that is very important concept when you talk about Debye Huckel theory. I am gradually going to the background of Debye Huckel theory, because we are considering non-ideal solutions, because normally in the case of electrolyte solution is fall under this category. So that is why we need this term called activity and activity coefficient. Okay, so I will next I will tell you one hypothetical condition of this difference between ideal and non-ideal in terms of this activity coefficient, and gradually after that I will go to the Debye Huckel theory. So we will see the one of the imaginary situations where the activity coefficient plays a very good role. Okay, you can also call it as the interpretation of activity coefficient. That means you can also interpretation of activity coefficient. So I am considering two situations. I am going to consider two situations here. One is a non-ideal situation, and other one is an ideal one. Okay, the non-ideal what I am drawing is a solution where the charge is present. So for our convenience, I am just showing the positive charge, positive charge. You know that if positive charge is there, there is also negative charge. So I am not highlighting that negative charge, it is there. Okay, so this is our charged solution, and I am taking another situation that is actually a hypothetical situation. The beaker consists of the same number of ions. It's not in order. I'm just drawing like this for my convenience. You can see that charge is absent here. You can write that charge switched on here. And here the charge is switched off. That is why I am telling that it's an hypothetical condition. So this is non-ideal and that is the ideal condition. So we have already that these type of equations already we have discussed. That means what is the chemical potential of ideal case and non-ideal case. So in the case of charged system, just like our electrolyte, what is the situation? It's a non-ideal situation. You see, non-ideal situation. So where what is the equation for the chemical potential? Chemical potential A. Chemical potential A is equal to mu 0 A plus RT ln A, concentration of A plus RT ln gamma A. Okay, so what is the situation here? So I told you that this is a very imaginary situation where the charge is switched off. That is the ideal case. So ideal case, in ideal case you can simply write this mu A is equal to mu 0 A plus RT ln A. Okay, so now I am considering the difference between these two. That is known as the delta G. That is known as the delta G mix. So I am writing this one, delta G mix. What is this delta G? I will write here. What is this delta G mix? Delta G, there is a free energy change. I am writing here. That means ideal minus non-ideal. Okay, so this equation is important. You see, ideal minus non-ideal. So what you are getting for this, that means delta G. What you are getting? Delta G is equal to minus RT ln gamma A. Okay, gamma minus RT ln gamma. Okay, so this is the term you are getting when you take the free energy difference between these two. Then we will further discuss on this factor and our real situation, that means electrolyte solutions. So I told you that electrolyte solutions, the behavior is just like non-ideal solution. So now ideal here, it is simply a hypothetical case. That means the charge switched off case. Okay, so once again you please look into this factor. Delta G is equal to minus RT ln gamma. Okay, you see this factor, suppose I am considering in the case of a non-ideal system. So because our systems are non-ideal. So in the case of non-ideal systems, our this factor, what happens to this factor, we will see. So already we discussed that in the case of non-ideal solutions, this gamma non-ideal for the case of non-ideal solutions, in the case of non-ideal solutions, this gamma is smaller than 1. This gamma is smaller than 1. So what happens to this equation, this term? You see this term, what happens to this term? Okay, this is smaller than 1. Smaller than 1 means this whole term will be negative. So you see what happens to this equation, delta G is equal to minus RT ln gamma. So gamma is smaller than 1 means this term will be negative, and this whole thing, sign of this thing will be positive. So now this delta G is equal to RT ln gamma. Okay, RT ln gamma. So it look like the system is not stabilized. What system I am telling? I am telling about this non-ideal system. This is our electrolyte system, and it will look like it is not stabilized. Okay, so you can see that delta G, there is a positive value, that is delta G is equal to RT ln gamma. So we can just see that ideal system is stabilized, but non-ideal system is not stabilized. What is the reason for destabilization of non-ideal system? What is in this system? You see, in the case of an electrolyte system, there will be positive ions and there will be also negative ions, and also there are another molecules called solvent molecules. Actually, this destabilization, we are telling this destabilization, that is actually due to the repulsion. That is actually due to the repulsion between the like ions, that positive anion to anion and cation to cation. Anion to anion there is repulsion, cation to cation there is repulsion. That is the main reason for the destability of the system. And but still I can tell you that, and also there are many negative things. That means solvent molecules are there. Suppose an anion moves, it will first meet solvent molecules. Okay, so because solvent molecule is a large number here, and then only he will meet the other type ions. Okay, so you see this factor, when considering this non-ideal case, electrolyte case, this factor delta G is equal to positive 1, that is RT ln gamma. That means it is not a stabilized, it look like a destabilized system. Okay, but still it is a stabilized system. You know that electrolyte solutions are very stable. So why it is stable? So I told you that this destabilization is due to the repulsion between the like ions. Okay, so you can think like this. Okay, so during the movement of this particular cation, it will, I told you that it will normally meet the solvent molecules. And there is also another chance, that means the next chance is it will meet the other ions. So the important thing here is the encounter of this particular ion is most probably with the dislike charge, not like charge. Okay, that means the this is the cation. During his movement, most probably, the probability is more, it will interact with the opposite charge. Okay, so the probability is very high. So you see, probability is very high, it will interact with negative charge, not the like charge. that is actually the reason for the stability of this system, even though it is delta G is equal to RT ln gamma. So it is stabilized by a factor, RT ln gamma. So you understand what I am telling. I will tell again what is the situation here. So here in non-ideal case you got this delta G mix, non-ideal and ideal difference, you got this one. And here in the case of a non-ideal solution, that means our consideration, that is electrolyte system, gamma is smaller than 1 and delta G is equal to minus RT ln gamma. Okay, so here this is simply not minus RT ln gamma, this become RT ln gamma. So it look like it is destabilized, but it is stable. So I am telling what is the reason for the stability of the system. Okay, so destabilization is due to the repulsion. But suppose when you are considering a particular positive ion, during his travel or during his motion, normally it will interact with the probability of interaction with different ions, that is the opposite ion is more compared to like systems, like charges. That is the reason, that is the main reason for stability of this particular system. So there comes a very important idea, another to account the stability of the system, that is the idea of ionic atmosphere. So all these concepts, that means what is the concept here? That means in his motion, in his travel, it will most probably the probability of meeting with different ions is more compared to the like ions. That is one of the reasons for stability of the system, even though the value is like this. Another important idea here comes, how the system stabilizes. The answer is the ionic atmosphere, the possibility of forming an ionic atmosphere. So let me see what you mean by ionic atmosphere. So now we reached we gradually reached the Debye Huckel theory. It actually told us about the ionic atmosphere. That means how the system is stabilized, and what are the factors mainly affecting the ionic atmosphere. So that is our next discussion. We'll see one by one. Okay, so first we'll just see what is the ionic atmosphere and what are the factors that is affecting the ionic atmosphere. So that is our next discussion. That means we are gradually reaching in the Debye Huckel theory. Okay, let me see what is this. Okay, so very important concept I already introduced, that is the concept of ionic atmosphere. So this is also one of the reasons to the stability of the system. Okay, so ionic, we will see what is ionic atmosphere. Suppose you have a positive ion in the solution, there is a cation in the solution. You can see that the negative ions will form a spherical shape around this cation. That if you draw like this is not a two-dimensional type drawing. You can consider this as a three-dimensional system. Positive charge is surrounded by the negative ions, just like a globe. Okay, just like a dandelion, you can see. Okay, you can see like this. Okay, so here you can also write for the next anion, that's delta plus. You can see delta plus, again delta plus, you can see this is also another ionic atmosphere. So the formation of ionic atmosphere, that means this positive ion is always encounter, most probably it is probable encounter is with a negative ion. So that means it will form an ionic atmosphere. So that is the reason for the stability of this non-ideal system, or the stability of the electrolyte. Okay, so in another way I can tell you, in a practical sense I can tell you what are the factors that disturbs the ionic atmosphere, and from that how can you quantify the term called activity coefficient. You see, I am considering a cell, a zinc copper cell, zinc 2 plus and copper 2 plus copper. I am considering a zinc copper cell. The cell potential of this one is 1.1 volt. 1.1 volt. Suppose I am adding a small amount of lithium chloride. Suppose I am adding a small amount of lithium chloride in the copper 2 plus compartment. Copper 2. What is the situation here? We have this copper compartment here. I am just adding a small amount of lithium chloride into the copper compartment. What happens? The cell potential will become decrease. It will become 1.05 volt. It decreases. Okay. Also, lithium chloride you can add to this compartment also. You can add zinc compartment. You can also add. Suppose you add in the zinc compartment, it will become, again it will reduce, but it is a little bit higher compared to this another compartment. It is still 1.08 volt, not 1.1 volt. So why this reduction happening? Okay, so I am adding more ions to the system, that affects the cell potential. So why it is happening? You see, in the copper compartment you have this copper 2 plus ions, and that will make an ionic atmosphere. With the negatively charged ions. When you are adding LiCl, that means Li, lithium plus Cl minus ions, what will happen? There will be formation of another ionic atmosphere. So normally you see that Cu2 plus and Li plus will repel, and there will be attraction also. It is there, attraction terms are also there, but repulsion terms are also there. Okay, so here when you are adding LiCl to the system, normally what will happen? Normally the motion, usually you see in this type of zinc copper system, cell, it has to move. These ions should carry the charge. That is important. Should carry the charge to the electrode. So this motion is little bit screened by when you are adding a small amount of LiCl. That means more number of ions means the movement of Cu2 plus will be restricted. That means it cannot show its effective charge. That means it is a disturbance to this ionic atmosphere, and actually there is a screening effect. That particular effect is called screening effect. So due to this screening effect, what happens? Cu2 plus, the effective charge, it cannot show its Cu2 plus effective charge. That is why the cell potential is decreasing. and here also the same thing happening. The cell potential is again decreasing. This is known as the ionic screening. Okay, so I am talking about the ionic disturbance for the ionic atmosphere, and this is also called the ionic screening. So many things we have to consider. I told you that we have started from gamma plus minus, that is a mean activity coefficient. So in order to evaluate this quantity, we need some additional parameters. Some additional parameters, one of the important additional parameters here is known as the I, or it is known as the ionic strength. Because I told you that here the number of ions, what happens when number of ions in the system increases. So we need another term called ionic strength. I already told you about ionic strength in the last class. You can check my class on activity and activity coefficients. This ionic strength is equal to half into sum of Ci Zi square. So what are the terms? I am not explaining in detail because we already discussed. Ionic strength I is equal to the concentration. C is the concentration and Z is its charge. So you have to emphasize on the charge also. So in order to find out this term, that means gamma plus minus, surely you need ionic strength. So by ionic strength you can effectively explain this, account this ionic atmosphere. So that important term is called ionic strength. Then we will just see what is the equation for the Debye Huckel theory. What is the important equation coming from the Debye Huckel theory? So I am not going to the derivation. The derivation of Debye Huckel theory is actually very complicated. If you love mathematics, you can just look at the derivation of Debye Huckel theory. Actually, we does not need this derivation here. We can just interpret the equation derived out from the Debye Huckel theory. Okay. So I told you about this term ionic strength. Ionic strength is very important. You can see the ionic screening effect. So from that you can understand this term ionic strength is very important. The equation, I told you that you need Debye Huckel theory for finding out this mean activity coefficient. So the equation is log base 10 gamma plus minus, that is the activity coefficient is equal to minus a z square into root I. So this is the Debye Huckel. This is the equation from the Debye Huckel theory. So I told you, now we can you can see that you can find out this thing. Okay. So what is this thing? So we can just discuss what is this A is a parameter. That depend upon temperature and solvent. A parameter depend upon temperature and solvent. What is Z? Why you are writing this Z square? You can also write like this log 10 gamma plus minus is equal to minus a z plus z minus mod of z plus z minus into root I. That is also correct. You see. So these are the Z is the charge. Sorry, I'm sorry. I can write here Z plus. Normally you will write here Z plus Z minus. Alright, Z plus and Z plus, Z minus. So this is equation from the Debye Huckel theory. So here you can see the important term called ionic strength. Okay, so ionic strength is needed to explain all these things. Okay, so what is the peculiarity of this equation? Suppose you plot log gamma plus minus, log gamma plus minus, that's mean activity coefficient, versus root I, it will be a straight line, because it's a straight line type equation. Okay, so your electrolyte, if your electrolyte is obeying Debye Huckel theory, means it will be a straight line. So but that will be obeyed by a very dilute solution. If your solution is little bit concentrated, that means if it is not very dilute, it will not obey Debye Huckel theory. Okay, so Debye Huckel theory is obeyed by very dilute solutions, but you know that in our electrolyte solutions are not much dilute. So we have to consider the concentrated situation also. What happens when the electrolyte is concentrated, that also you have to check here. Okay, so this is the ideal case. You will be getting a linear type graph according to the equation. So we will just check how the electrolytes are deviating from Debye Huckel theory sometimes when the concentration is very high. So what happens when the concentration is very high? Okay, you see, I already told you this linear graph. This is for very dilute solutions. So you can expect this type of a graph in the case of a very dilute solution. Okay, very dilute solution. When the concentration is little bit high, means what happens? We'll see. So here the concentration high means a little bit high, or it's if it is not a very dilute solution, we will see what happens to the ionic atmosphere. So I already showed you the ionic atmosphere like this. This is one charge and surrounded by another charge. So if it's a positive, the negative charge you can see here. Okay, so when the concentration is high, what happens to the ionic atmosphere? The ionic atmosphere will shrink. Okay, the ionic atmosphere will shrink because there are solvent ions. The solvent ions will become decreases. And the ionic atmosphere become shrink at a high concentration. So you can consider a very important parameter here, that is called A. I am just expressing it as A. A is actually known as the Debye length. Okay, A is known as the Debye length. So Debye length will be changing when the concentration changes. That means for high concentration, the Debye length will be very small. So it will normally affect this curve. That means this equation. That means you see this Debye length. I told you that the concentration high means what? Concentration high means it is also means that ionic strength is high. That means your Debye length A is inversely proportional to the ionic strength. Inversely proportional to the ionic strength. Okay. So in this situation, what happens? I will draw our curve, Debye Huckel curve. That is the log gamma plus minus versus root I. I am drawing this. Okay, so I already told you here you are getting a straight line in the case of very dilute solution. That is why this particular theory is known as Debye Huckel limiting law. L is for limiting law. So this particular straight line, which we are getting this is the line, it's a border line. See, I'm just plotting a broader line here. Suppose you are getting like this, means it's ideal, and there is a limitation. That means there is a concentration limitation. This is called DHL. That means Debye Huckel limiting law. So what happens in this case? In this case, you have to when the concentration increases. Normally the graph is little bit, it will deviate like this. That means during the high concentration, it just show a style like this. Okay, I think you can see this. It will go like this. That is this particular curve can be explained by another equation, another law is known as extended Debye Huckel law. So that is the effect of this ionic atmosphere shrinking. So in the case of extended Debye Huckel law, you can write this equation, that is the log gamma plus minus is equal to minus a z square root i divided by 1 plus ba into root i. So this is the equation. So accounting this A. So at high concentration, you can write the behavior of the curve you can explain like this. This is called the extended Debye Huckel law. Log gamma plus minus is equal to minus a. So additional parameters coming here is one is B. B is also a temperature solvent parameter, and another one is A. A is the Debye length, not activity here. Please not confuse about that. This is called Debye length. I'm just giving A, B A into root I. So this here we accounted the Debye length. So normally you see we are dealing with this type of solutions. That means somewhat concentrated solution, not very dilute. So Debye Huckel will be obey in this particular range only. That is why it is known as Debye Huckel limiting law. So when you further increase the concentration, the effect is it will become like this. That means it touches this border line. It will go like this. Okay, it will go like this. So when the concentration increases more, what happens when the concentration increases more? We'll see. Okay, concentration increases more means the solvent also will play a very good role here. Okay, so you have to introduce another term for the solvent to account this. Such type of a model is to explain this Robeson-Stocks model. So there one additional term is coming in this equation in the case of a Robeson-Stocks model. So they accounted this particular behavior by introducing another term in this equation. It is like this. This equation is like this. Log gamma plus minus is equal to our, this term is there, minus a z square root I divided by 1 plus ba root I plus c into I. That is the another term they introduced. C is related to some solute solvent interaction. Solute solvent, because solute solvent interaction will be more in the concentrated solution. So it is a parameter related to solute solvent. This is our ionic strength. So just like this one, we have different models, and normally there are deviations from the Debye Huckel theory. So you see, we have started from the background of Debye Huckel theory. That is, the real background is activity and activity coefficient. So when we are considering non-ideal solutions, that means when we are considering the electrolyte solutions, we need the concentration term activity. So activity is related to the activity coefficient. So activity coefficient is a very important term we have to define. So that is an attempt by Debye and Huckel, and they proposed the theory to find out this activity coefficient, and many terms will come. You see, ionic strength is coming from the ionic atmosphere, so that I already explained you. So when you are you can understand if you have a very good idea about activity and activity coefficient. So for that, you can see my previous class on activity and activity coefficient. Please read about the Debye Huckel theory well. Thank you.